everyone, and today we are going to learn about the conductance and its application measurements. What is conductance? Conductance implies the ease with which electric current can flow through a conductor. It is defined as the reciprocal of resistance. So conductance is given by 1 upon R, where R is the resistance. Next, conductance is expressed in units of reciprocal or inverse ohms. In SI unit, the unit of conductance is Siemens or Mohs. Strong electrolytes, example, NaOH, HCl, NaCl dissociates completely. Hence, more number of ions are present in solution and hence more conductance. Therefore, conductance depends upon number of ions. More the number of ions, that is, more conductance. Less the number of ions, less is the conductance. Next is the application of conductance measurements. So there are a number of direct applications of conductance measurements. Some of them are determination of ionic product of water, determination of solubilities and solubility products of sparingly soluble salts, and conductometric titrations. First, let us see the determination of ionic product of water. The product of concentration of H plus and OH minus ions in water at a particular temperature is known as the ionic product of water. It is designated as Kw. We know that water is a weak electrolyte. The dissociation equilibrium of water can be considered as H2O plus H2O, which gives H3O plus OH minus. Here we have two water molecules, wherein one water molecule is accepting proton and producing H3O plus, wherein the other water molecule is donating proton and forming OH minus ion. Next, H2O gives H plus OH minus, and we get the equilibrium constant as H plus OH minus divided by H2O, the product divided by the reactant, where H2O is taken as constant. So the final equation which we get is Kw is equal to H plus OH minus, which is the product of concentration of H plus and OH minus ions, where Kw is the ionic product of water. At 298 K, Kw is equal to 1 into 10 raised to minus 14 mole square dm minus square. Next is the determination of solubilities and solubility products of sparingly soluble salts. If S is the solubility in mole per liter of a sparingly soluble salt and K is the specific conductance of the saturated solution, then its molar conductance lambda is given by the relation lambda is equal to 1000 K upon C. If we take this C up, we get it as C is equal to 1000 K upon lambda m. At infinite dilution, S is equal to 1000 K upon lambda infinity m, where K is the specific conductance, lambda is equivalent conductance at infinite dilution, C is the concentration in grams equivalent per liter, and S is the solubility. If we take AgCl, which gives Ag plus Cl minus ions, if the equilibrium constant is taken as Ag plus Cl minus divided by AgCl, so product divided by the reactant. So here AgCl is taken as constant. So the final product what we get is Ksp is equal to Ag plus Cl minus, where Ksp is equal to the solubility product constant. Conductometric titrations. Conductance measurements are frequently employed to find the endpoints of acid, base, and other titrations. In such titrations, variation of equivalent conductance by the addition of titrant is measured. In conductometric titrations, advantage is taken on the fact that conductivity of a solution is dependent upon the number of ions in their conductance. So there are different types of conductometric titrations. First is the strong acid versus strong base. Second is the strong acid versus weak base. Third is the weak acid versus strong base. Fourth is weak acid versus weak base. And the fifth is the mixture of a weak acid and a strong acid versus strong base. So let us see each one of them in details. Titration of a strong acid with a strong base. Titration of a strong acid like HCl with a strong base like NaOH. So we know that HCl in aqueous solution is a strong electrolyte. The conductance of HCl is due to the presence of hydrogen and chloride ions. So, as the alkali, that is, the NaOH, is added gradually, the hydrogen ions are replaced by slow moving sodium ions with low ionic conductivity. On continued addition of NaOH, the conductance will go on decreasing until the acid has been completely neutralized. So, we can see that here the conductance is decreasing. So after the equivalence point, excess NaOH is added. Here now there is an accumulation of OH minus ions with high ionic conductivity, and therefore the conductance increases. So this is a graph which we get for the titration of a strong acid with a strong base, and this is the equation. HCl plus NaOH gives Na plus Cl minus plus H2O, and this is called as the equivalence point. The second type of titration is the titration of a weak acid versus strong base. Titration of a weak acid like acetic acid with a strong base like NaOH. Acetic acid does not dissociate due to the common ion effect of CH3COO-. Therefore, there is a slight decrease in the conductance initially. Next, on further addition of NaOH, acetic acid is neutralized. After the neutralization proceeds, weakly ionized acetic acid is replaced by highly ionized sodium acetate. Therefore, there is increase in the conductance. When the acid is completely neutralized, further addition of NaOH in excess results in the fast-moving hydroxyl ions. Therefore, conductance increases sharply. Next is the determination of a weak acid with a weak base. Titration of a weak acid like acetic acid with a weak base like ammonium hydroxide. Conductance of CH3COH is very low due to low ionization. On addition of NH4OH in acid solution, conductance slightly decreases. So here we can see there is a slight decrease in the conductance initially. This is because of the substitution of H plus ions by NH4 plus ions. On further addition of NH4OH, that is the ammonium hydroxide, increases the conductance till the end point is determined. So here you can see there is a increase in the conductance. This is due to the increase in concentration of the ammonium acetate salt which are produced, which is highly ionized. After the end point, there is no increase in conductance due to a very small amount of ionization. So here at the end you can see there is no increase. Okay, it is constant. The last type of titration is the titration of a mixture of a weak acid and a strong acid versus strong base. So here two acids are titrated against the strong base, that is the NaOH and HCl. HCl, being much stronger, will get titrated fast. The presence of a strong acid ionization of a weak acid is suppressed due to common ion effect. So strong acid is neutralized first, followed by a weak acid. Therefore, the first point of intersection refers B, that is B, refers to the neutralization of a strong acid, and point C refers to the complete neutralization of an acid mixture. The titration of acetic acid will commence only after HCl has been completely neutralized. Solve the first problem. At 25 degrees Celsius, the specific conductance of a saturated solution of AgCl is 2.68 into 10 raised to minus 4 Siemens meter inverse, and that of water with which the solution was made is 0.86 into 10 raised to minus 4 Siemens meter inverse. If the molar conductance at infinite dilution of AgNO3, HNO3 and HCl are 1.33 into 10 raised to minus 4, 421 into 10 raised to minus 4 and 426 into 10 raised to minus 4 Siemens meter inverse respectively, then the solubility of AgCl in grams per dm cube in water at a given temperature is, here are the options, and let us solve this problem. Okay. So first let us write what is given. So we are given that the specific conductance of the AgCl is 2.68 into 10 raised to minus 4 Siemens inverse, and that of water is 0.86 into 10 raised to minus 4 Siemens inverse. So we use this formula, that is K solution is equal to K AgCl plus K water. Next we are going to substitute the values and we get the specific conductance of AgCl is 1.82 into 10 raised to minus 4 Siemens inverse. Next, using Corrach's law, lambda naught m AgCl is equal to lambda naught m AgNO3 plus lambda naught m HCl minus lambda naught m HNO3. We substitute the values and we get the answer as 1.38 into 10 raised to minus 4 Siemens meter square mole inverse. Next, we use the solubility formula, that is the 1000 K upon lambda naught M. So 1000 into, we got the specific conductance of the AgCl as 1.82 into 10 raised to minus 4. So we are going to substitute it over here, divided by the lambda naught M, that is 1.38 into 10 raised to minus 4. And we get the answer as 1.3188 mole meter minus 3. So the final answer is 1.31 mole inverse minus 3. What is the value of the ionic product of water at 298 K? So here are the options, and the correct answer is 1 into 10 raised to minus 14 per mole square liter square. The next one is, the graph shown below is a graph for conductometric titration of, here are the options, and the correct option is weak acid versus strong base. Next problem, if the specific conductance of sparingly soluble salt in the ratio 1:1 and the molecular weight is equal to 200 gram mole inverse in its saturated aqueous solution at 25 degrees Celsius, and that of water are 1.5 into 10 raised to minus 3 ohm inverse dm inverse and 1.5 into 10 raised to minus 5 ohm inverse dm inverse respectively, and the ionic conductance for its cation and anion at infinite dilution are 0.485 and 1 ohm inverse dm inverse mole inverse respectively, then the solubility in gram liter inverse of the salts in water at 25 degrees Celsius is. So these are the options. This is the same problem as the first one. You all can solve this on your own, and this is the solution. So let us solve the last problem. For the graph shown below, if the first endpoint for strong acid is at 4 ml and second endpoint for weak acid is at 10 ml, then the volume required for the neutralization of the weak acid in the mixture is, let us see the options. So first is A is 10 ml, B is 6 ml, C is 4 ml, and D is 2 ml. So if suppose this is the first endpoint, that is the 4, and this is the second endpoint, that is the 10. Now to find the volume required for the neutralization of the weak acid, we have to take 10 and subtract it with 4 to get the answer. So the answer is 6 ml. Thank you.